how balance turns into collapse without warning. Everything seems perfectly balanced. Forces cancel out, systems hold steady, and then, suddenly, balance disappears. To understand how balance turns into collapse, we need to stop thinking of balance as strength. Balance is a condition, not a safeguard. It exists only as long as opposing forces remain matched within narrow limits. Outside those limits, balance offers no protection at all. The equilibrium we celebrate is often far more precarious than it appears. What we perceive as stability is frequently just a temporary alignment of forces that could shift at any moment. The illusion of permanence emerges from observing balance during favorable conditions, leading us to mistake circumstantial alignment for structural integrity. This confusion between temporary states and enduring properties lies at the heart of why balanced systems fail so catastrophically. We build confidence from calm periods without recognizing that calm itself may be eroding the very capacity to handle turbulence. This matters because many systems are designed to sit precisely at balance. Markets match supply and demand. Power grids balance load and generation. Ecosystems balance growth and decay. When these forces align, performance looks optimal, efficient, elegant. Engineering celebrates these achievements as pinnacles of design. Economic theory treats equilibrium as a natural resting state toward which systems gravitate. The mathematics of optimization consistently pushes systems toward tighter balance, rewarding precision and punishing deviation. This creates powerful incentives to engineer systems that operate at the finest possible tolerances, maximizing output while minimizing waste. The logic appears unassailable. If balance represents efficiency, then perfect balance represents perfect efficiency. But this reasoning ignores a crucial dimension. It treats balance as purely beneficial, while overlooking what is sacrificed to achieve it. But balance hides tension. Opposing forces are not gone. They are locked in place. Energy accumulates silently on both sides. As long as nothing shifts, the system holds. But small changes matter far more than they appear. The forces pushing against each other do not diminish simply because they cancel out. They remain active, straining, ready to surge the moment constraints loosen. This stored tension is invisible to standard monitoring. Sensors measure net outcomes, not underlying pressures. A system can appear perfectly stable while internal stresses build toward critical thresholds. The absence of visible motion masks the presence of enormous latent forces. When balance finally breaks, observers are shocked by the violence of the response, not realizing that the energy was accumulating all along, hidden by the very equilibrium that seems so reassuring. At first, disturbances are corrected instantly. A little more input here, a small adjustment there. Balance is restored. Confidence grows. The system feels self-correcting, almost invincible. Each successful recovery reinforces a belief that balance is sustainable, that the system has mastered its environment. Control mechanisms respond smoothly. Feedback loops operate precisely. Deviations are caught early and neutralized before they propagate. This phase generates tremendous institutional confidence. The system appears to have found its ideal operating point. Managers congratulate themselves on fine-tuning. Engineers celebrate their calibration. Economists point to efficiency metrics that confirm optimal performance. The track record of successful corrections becomes evidence that the system can handle whatever comes next. Yet every correction tightens coupling. Dependencies deepen. Flexibility fades. The system becomes excellent at maintaining balance under expected conditions, and terrible at adapting when conditions change. Each adjustment, while successful in restoring equilibrium, simultaneously narrows the range of conditions under which equilibrium can be maintained. Feedback mechanisms that correct small deviations become incapable of handling large ones. The precision that enables rapid correction of minor imbalances creates brittleness when facing major disruptions. Control systems optimize for one operating regime fail catastrophically when that regime shifts. This paradox is rarely recognized because the strengthening of narrow capabilities and the weakening of broad adaptability happen simultaneously and invisibly. The system grows more competent and more fragile at the same time, with only the competence visible in day-to-day operations. Eventually, a point is reached where balance can no longer be maintained. not because forces grew large, but because adaptability vanished. The system cannot redistribute stress. Balance gives way, not gradually, but abruptly. The transition happens faster than adjustment mechanisms can respond. One moment, everything is under control. The next moment, control is completely lost. There is no intermediate phase of manageable difficulty. The system operates normally until it cannot operate at all. This binary character makes balanced systems particularly dangerous. They provide no grace period for intervention. When problems appear, they are already catastrophic. The smooth operation that preceded collapse offers no preparation for the violence that follows. Organizations built around maintaining balance have no institutional memory of handling its absence. Collapse does not begin with imbalance. It begins when balance becomes rigid, and rigidity is what makes collapse sudden. As systems operate near perfect balance, their behavior becomes deceptively smooth. Fluctuations are dampened. Variability shrinks. Everything looks controlled. This calm is often mistaken for resilience. Observers watching stable metrics conclude the system is robust. The absence of visible stress is interpreted as the absence of vulnerability. Performance reviews celebrate the consistency. Stakeholders reward the predictability. The steadiness becomes its own justification, proof that the approach is working. But this interpretation confuses symptoms with causes. The smoothness is not evidence of strength. It is evidence of operating conditions that have not yet challenged the system's actual limits. The calmness reflects not resilience, but the absence of tests that would reveal brittleness. Mathematically, this is a warning sign. Systems near critical balance lose the ability to dissipate energy gradually. Stress is stored instead of released. Small disturbances no longer fade. They travel through tightly coupled components. The mathematical signature is unmistakable to anyone looking for it. Response times slow, correlations increase, variance builds in ways that should trigger immediate concern. But these signals rarely generate action because they appear during periods of apparent stability. The system still performs its functions. Outputs remain acceptable. Nothing has failed. The mathematical indicators of approaching catastrophe compete with experiential evidence of continued success, and experience typically wins. Decision-makers trust what they can see over what models predict, especially when predictions suggest disaster, while observation shows normalcy. This creates a fragile equilibrium, a state where stability depends on nothing changing. The system can tolerate no surprises, no delays, no mismatches. Performance is high, but tolerance is low. Operating margins that once absorbed variation have been eliminated. Backup capacity that once provided safety has been reallocated to production. Redundancies that once allowed graceful degradation have been removed as inefficiencies. The system has been optimized into a configuration where everything must go right, because nothing can go wrong. This is celebrated as lean operation, as elimination of waste, as achievement of theoretical efficiency limits. But it is actually the construction of a trap. The system has been transformed into something that works brilliantly under expected conditions and fails catastrophically under unexpected ones. Near this point, cause and effect become disconnected. Actions have delayed consequences. Corrections overshoot. The system oscillates, then suddenly tips. From the outside, collapse looks instantaneous. From the inside, it was prepared over time. The disconnection between intervention and outcome destroys the ability to steer. Control inputs no longer produce predictable results. Attempts to stabilize create instability. Efforts to correct make things worse. The system enters a phase where human judgment becomes actively counterproductive because the relationships that judgment relies upon no longer hold. Operators find themselves in a situation where their training and experience lead them to take actions that accelerate rather than prevent collapse. The speed of deterioration outpaces the speed of comprehension, leaving everyone perpetually behind events they can no longer influence. What makes this phase dangerous is false confidence. Balance systems appear optimized. Metrics look perfect. Efficiency peaks. Warnings are dismissed because nothing seems wrong. Every indicator tracked by management shows success. Financial performance is strong. Operational metrics are excellent. Stakeholder satisfaction is high. There is no evidence of problems that would justify defensive action. Anyone raising concerns about hidden vulnerabilities faces the burden of proving a negative, of demonstrating danger in the absence of visible threats. This burden is rarely met successfully. The institutional momentum favors continuation over precaution. Systems that have operated successfully for extended periods develop powerful presumptions of continued success. Breaking through these presumptions requires either prophetic insight or catastrophic validation, and by the time catastrophe validates the warnings, the opportunity for prevention has passed. But mathematically, balance is not safety. It is exposure. The more precisely a system is balanced, the more violently it responds when balance is lost. The conflict erupts the moment balance is disturbed, and the system has no room to adjust. A small shift, once harmless, now cascades through every connection. Forces that were held in check surge simultaneously. This is the emotional peak, the shock of speed. Collapse does not unfold step by step. It happens all at once. Structures fail together because they were balanced together. There is no sequence, only a drop. The synchronized nature of the failure reflects the synchronized nature of the operation. Components optimize to work in perfect coordination cannot work any other way. When coordination breaks, everything breaks. The efficiency that came from tight integration becomes the mechanism of comprehensive failure. There is no graceful degradation because degradation was designed out of the system. There is no partial failure because partial success was not an acceptable operating mode. Mathematically, the system has crossed a tipping point. Feedback loops flip direction. Stabilizing forces become destabilizing. The same mechanisms that held balance now accelerate breakdown. Control systems that corrected deviations now amplify them. Safety systems that prevented small failures now trigger large ones. Communication networks that coordinated action now propagate panic. The infrastructure built to maintain stability becomes a highway for collapse. This reversal happens not through malfunction but through mathematics. The same equations that produce stability under one set of conditions produce instability under another. The system has not broken in the sense of ceasing to follow physical laws. It is following those laws into a different regime, one where everything that previously helped now hurts. What makes this moment so destructive is surprise. Because nothing appeared wrong, preparation never happened. Safeguards were trimmed. Buffers were removed. Redundancy was labeled inefficiency. The system trusted balance instead of adaptability. Emergency protocols designed for gradual problems are useless against sudden collapse. Response plans assume time for assessment and coordination. Training prepares personnel for escalating challenges, not instantaneous catastrophe. The organizational muscle memory is tuned entirely to maintaining balance, not to operating without it. When balance vanishes, the organization finds itself in a situation it has never practiced for and cannot improvise through. The speed overwhelms decision-making processes. The scope overwhelms response capacity. The surprise overwhelms psychological preparation. Intervention at this stage is nearly impossible. Corrections arrive too late or with too much force. The system responds violently to help, just as it responded violently to disturbance. Balance has turned into brittleness. Attempts to restore equilibrium create new imbalances. Fixes in one area trigger failures in others. The system has become so tightly coupled that no intervention is local. Everything affects everything else, making controlled recovery impossible. The only option is to let the collapse run its course, then rebuild from a state that has naturally found a stable configuration. This means accepting massive losses that might have been prevented if action had been taken earlier. But early action was never politically or economically viable because a case for it could not be made without the very collapse that validates it. The conflict is not between order and chaos. It is between flexibility and precision. And precision, pushed too far, leaves no room for recovery. The resolution begins when balance is no longer treated as a goal, but as a moment. Mathematics makes this clear. Systems that survive are not those that remain perfectly balanced, but those that move around balance without locking into it. This requires a fundamental shift in design philosophy. instead of seeking to minimize deviation from optimal points. Resilient systems accept deviation as necessary for long-term survival. The goal becomes not perfect performance, but sustainable performance. Not maximum efficiency, but robust efficiency. Not optimization, but optimization within margins that preserve adaptability. This shift feels like accepting defeat, like settling for less than is theoretically achievable. But it is actually choosing reality over theory, sustainability over peak performance. This changes how resilience is designed. Instead of holding forces in exact opposition, systems are allowed to fluctuate. Stress is released gradually. Imbalance is tolerated early, so collapse is avoided later. Buffers return. Slack is valued. Redundancy is protected. The system trades peak efficiency for survivability. What looks messy under calm conditions become stabilizing under pressure. These design choices cannot be justified by optimizing for normal operations. They only make sense when abnormal operations are weighted appropriately in the design calculus. This means explicitly valuing rare events, building capacity for conditions that may never arrive, maintaining capabilities that may never be used. Traditional cost-benefit analysis struggles with these choices because the benefits are hypothetical and difficult to quantify, while the costs are concrete and immediate. The deeper lesson is counterintuitive. Perfect balance is not strength. It is a warning sign that flexibility is gone. Stability comes from motion, not stillness, from the ability to adjust before adjustment becomes impossible. This principle applies across domains. Biological systems that survive are those that maintain diversity and redundancy. Ecological systems that persist are those that fluctuate rather than lock into equilibrium. Economic systems that endure are those that tolerate inefficiency rather than optimize it away. Social systems that adapt are those that preserve slack resources and alternative structures. The pattern is universal. Rigidity precedes collapse, while flexibility enables survival. Learning this lesson requires overcoming deep intuitions that equate stability with motionlessness and efficiency with virtue. Collapse feels sudden only because preparation was invisible. Balance failed not because it was wrong, but because it was treated as permanent. Understanding that difference is what separates systems that recover from systems that fall apart without warning. Subscribe to join the journey.